Hi everyone. Today I'll be doing a fairly informal video where I am going to add a low dropout regulator to an existing design. For this design currently, I have a USB-C plug connection into a battery charger, and that battery charger is going to charge a LiPo battery, and I need to convert the LiPo voltage into a voltage that this processor, this STM32L422K, can take. So looking at the datasheet for my STM chip, I can see that it is expecting a 1.71 volt to 3.6 volt power supply. So a voltage of 3.3 fits in the middle there, and is a relatively common voltage to power different devices at. So I will be doing 3.3. And just to make sure, we can check the power section of the datasheet. That this is kind of just the quick facts of the datasheet. And we can see power supply management section. And we have the power supply schemes. So VDD is expecting that 1.71 to 3.6. And all other bus voltages are within that. 3.3 is within that range as well. So 3.3 is a good candidate. We can check the absolute maximum ratings just to make sure 3.3 is not exceeding any ratings, which in this case it isn't because it already is specified, but absolute maximum ratings you generally want to stay away from because they can stress the part if you operate the device at those ratings. So the device might work, it might not, but either way, you kind of lose the guarantee of working that the datasheet provides. So you might get some unintended behavior. So going back to KiCad, I have a LiPo battery, and LiPo batteries, what they do is at full charge is 4.2 volts. No charge is around 3.6 volts. So depending on how charged my battery is, I am going to have an input voltage to my LDO, low dropout regulator, of from 3.6 volts to 4.2 volts. So I need to choose a regulator with a dropout voltage of less than 300 millivolts. The dropout voltage is going to be V in minus V out. So for a linear regulator, V in is going to be strictly higher than V out. And my worst case V in is going to be 3.6 volts. And I am going to have a fixed output voltage of 3.3 volts. So I'm going to have a voltage difference between V in and V out of 300 millivolts. And one thing to always take care of when you're using a linear regulator is the power dissipation, because linear regulators are dissipating the voltage drop as heat. So one thing is my expected max current is going to be around 100 milliamps. It's actually going to be less than that, but this is a overestimate on purpose. If I look, the worst case voltage drop is going to be when the LiPo battery is at full charge. So I have 4.2 volts minus 3.3 volts equals 900 millivolts. And my power equation is P equals IV. So we are going to have 900 millivolts times 100 milliamps, and that is equal to 90 milliwatts. So when the LiPo battery is fully charged and I am drawing 100 milliamps from the regulator, I am going to be dissipating 90 milliwatts as heat in the regulator. And 90 milliwatts is not too bad. most, if not all, regulators can handle that. But it is something good to be aware of. So I'm just going to put these considerations right here. And now we can look for a regulator. So I'm going to use ti.com, Texas Instruments, because I work there, so I'm kind of bound by honor to use their parts. So if I drop down on the products, I can see a bunch of different sections. The one that I want in specific is power management. Now we get more sections. The regulator I want is the linear and low dropout regulators. So for the LDOs, it looks like they split it up into low VN, mid VN, and wide VN. My VN, we already know, is going to be 4.2 volts to about 3.6 volts. So that falls within the low VN category. And then we have some more subcategories. For now, I'm just going to search for all. So we are greeted with this table showing a lot of different regulators. So one thing I know is I don't want an adjustable output. I want a fixed 3.3 volt output. So right off the bat, I can say I want fixed output. No programmable, no tracking, no negative, no dual output. And I know what my output should be. It should be 3.3 volts. If I wanted a stranger output, like 3.812 volts, then I might need to use an adjustable output and set that voltage using a pair of resistors. But I want a commonly used output. Next thing I want to check is that the Vin min and Vin max, I fall within that range. So I can operate this device between 1.4 and 5.5 volts. That I fall within, so that is good. And I see this package, the SOT23, that's a nice hand solderable package. So if I click on this, I can see it's a 50 milliamp small size, high PSRR, power supply rejection ratio, low dropout regulator. And right off the bat, I can see I made a mistake. This is a 50 milliamp output. So basically, if I ask for more current than that, this part might not be able to supply that much current. And if we go back to here, I was expecting a max current of about 100 milliamps, which is greater than 50 milliamps. So this guy, it meets a lot of the criteria, but not all of them, so I can't go with it. But it does seem to have another device in the series. It actually looks like at least 3 devices in the series that are all pretty similar, but the only difference is how much maximum current they can provide. So this one, the TLV771, can supply 150 milliamps, which is greater than my expected max draw of 100 milliamps. If I wanted to be even safer, I could have like a safety factor of 3x instead of 1.5 and go with the TLV773 that can supply 300 milliamps. And the difference between these parts is most likely going to be in the price, which we can see we have 1.6 cents per killer unit, then 1.7 cents, and then 1.8 cents. So if I was buying 1,000 of these, I would be saving money by buying the less powerful one. So as the output current capabilities increase, as does the price, which is totally expected. So I see that it's not really too much of a jump, so I'm actually going to go with the TLV773. Get that higher safety factor with a marginal increase in cost. And we can see the Vout max is 3.3, and all my other ranges are fine. Let's look at the datasheet. And this just reconfirms what I was looking at before. So V in range, we fit within that range. We have a fixed output voltage range of 0.6 to 3.3, and that is going to be depending on what type I get, what option I get. So there should be different options. So if I go on the TI site, it looks like we can see some of those different options, but TI only lets you buy in order quantities of 3,000 at a time. So it would be good if I check Mouser. And I am going to check the part. And I'm going to check the part to see if it is available and in stock. So we can see we have my package I want, and then we have different output voltage options with 3.3. And we have, we are able to buy it in quantities of 1 unit. So I can buy something like 10, no problem. So it looks like this device is going to suit my needs. So let us see the supporting circuitry, which in this case is very simple. It's going to be just an input capacitor and an output capacitor. And it looks like both of those can just be 1 microfarad capacitors. And this is a 5-pin device. And the unit I want is a 5-pin device. So it has the input, the output, ground, an enable, and a no connect. And no connect just looks like it's best if I connect it to ground. And if I look for the dropout voltage, for my package, which is DBZ, let's confirm that. The 5-pin SOT23 is DBV. The dropout voltage at 300 milliamps is going to be around 200 millivolts. So already that is still within my range of 300 millivolt dropout. And mind you, that is at an output current of 300 milliamps. So if we look, there might be a graph that shows different dropouts for different I-outs. This is dropout voltage plotted as a function of output current. So my output current is going to be close to this value of 100 milliamps max. So if we look, the worst case is when it's at 125 degrees C. And if we just say 120 milliamps, it looks like my dropout voltage is 100 millivolts. So we're well within that range of 300 millivolts. So this looks like a good part to use. So I'm going to go back to KiCad and add symbol. Let's see if it appears by base. It does not, so that means it's not in the project library. If I look, we do have a variant of it, the TLV 70012. It looks like a slightly different variation of it. Let's see if we have one that just says 3.3, just for... So what I could do one of two things. I can edit this part to match the description of the device I'm going to use, or I can make a totally new symbol in the library, and anytime I want to use the 773, I'll have access to that symbol. For speed, I'm just going to edit this symbol. So we are the 773. Package is correct, SOT23 5-pin, and I am going to change this to 300 milliamps. It's a fixed output of 3.3 volts, and I'll even link the data sheet. So now we have our part. So let's add the supporting circuitry, the external components, which are just 2 capacitors. Let's do 1 microfarad. And for capacitors, I like to use 0603. We add 1 on input and 1 on output. And let's see what we need to do with this enable pin. So back to the datasheet. In the pin description, enable input, a low voltage on this pin turns the regulator off. So it looks like we want to have this tied high. So I am going to tie in to enable. So that's going to be our V in. So the part should always be enabled. Then I am going to place ground connections. And this, the input is the battery voltage, and the output is going to be 3.3 volts. So I'm going to add the symbols for that. 3.3 output. Hit save. I'm going to keep my calculations here, just for reference for people that are viewing this schematic. They can see kind of where my headspace was at and fact check any of my calculations to see if I'm gone crazy. And now we can add it to the PCB. So I'm going to switch to PCB editor. Going to update my PCB, and that added 3 parts. Perfect. So we can see my USB connector, we can see the battery charging IC, and now we have my LDO. So first thing I'm going to do is I have my battery voltage on the left, so I'm going to place the battery terminal on the left, put my capacitor here. My output capacitor is going to be on the right. Let's actually spin this one more time because I have the enable pin as well on the left. And I can connect my battery. Let's use a thicker track. I can connect grounds, and I am planning on having a ground plane. So let me get that situated. So I'm going to use a via to access a ground plane. This terminal, it did say to connect to ground. So I'm going to change the net name here into ground so I can make that connection. You saw before, it kind of prevented me from making the connection because it sees that these are 2 different nets. So I just edited the net so I can connect this pin to ground. Finally, we have the battery voltage. I could do one of 2 things here. I could snake this around, kind of similar to that, and that works. But for me, I'm just going to play it a little bit safe, and let's say I connected the enable pin incorrectly, and it should be go to low voltage. If I connect it like this, I give myself an out basically where I can cut this trace, and I just clean this up a little bit. There we go. I can cut this trace and tie the enable low, or even change where the enable signal goes. But if I routed everything underneath, I wouldn't have access to cut the trace without desoldering the device and making small cuts. Where here, I have a nice area I can cut right here. And finally, let me just add that ground plane. So we can see all these grounds have the rat nest lines showing that they should be connected. And it looks like I missed a connection here. So now that's connected. And I can snake this like that if I felt like it. Generally, I don't like to place too many traces underneath small packages like SOT23s. Now I am going to make a ground layer. So it's going to be on the back copper, and the node is ground. And let me make just a quick square polygon. Like that. And it is B to fill in zones. And now all those ground rat lines have disappeared because ground is connected for all these parts at least. I would still need to do the connection for the USB-C plug as well as the LEDs and my processor. The processor isn't mapped yet though. One last thing before we are finished. If we look at the 3D viewer, currently the reference designator for C3 is intersecting with some of the pads for U2. So we're going to want to adjust these reference designators to be more like this, where everything is spaced out and you can see each one corresponds to just a unique device. So really quick, we can remove the front copper to better see the silkscreen. Silkscreen is this lightish beige yellow, and we're just going to move C3 to be here. And then for consistency, we can make C4 there. And now we have silkscreen intersecting with silkscreen, so I'm just going to move this P1 designator. So now when we view, we can see that C3 and C4, they're both designating unique components. We have the U2, and this U2 package is nice. It even comes with a pin 1 silkscreen designator. Same with this SOT 6 pin. And with that, we are done. So, despite this design being relatively simple, there were still some potential pitfalls that we could have fallen into with the input voltage, the output current, dropout voltage needs to be high enough. So it's good to take things methodically and slowly and make sure you're just ticking all the boxes, fact-checking yourself, double-checking things, asking for advice, and doing external research. So the reason I knew to look for all these things and where to look in the datasheet and everything is just due to experience and simply making mistakes and then learning from those mistakes. So if you want to learn, I think it's a really good idea just to try your hand at making some of these designs. They can be on printed circuit boards, or they can even be on breadboards, and just testing them and seeing if they work. And if they don't work, try to figure out why. But that kind of experience is simply invaluable to any aspiring electrical engineer. So thank you for watching the video, and I hope you learned something.